So I'm just letting everyone in now.
All right. Hello. Good morning, everybody. I think we'll just wait another minute or two to see if we have any more people joining here, and then we'll get started here with Bill.
Morning or good afternoon.
Morning, good afternoon, good night. We have people from all over the world here on dialing in.
Hey Ben, sorry to jump the gun here. Will the recording be available for us to get after this training?
Yes, we will.
Awesome.
So what we'll do the hour call, we'll do the Q&A, and then Jennifer will be sending out the video afterwards today.
Awesome. Thank you.
No problem. Okay, I think we'll get started. If we have anybody else join, Jennifer, you can just please let them in as we get started. So thank you everybody for joining. As I said, good morning, good afternoon, and good evening to people. We're happy to welcome Bill Smith calling in from Phoenix, Arizona today. And welcome for the first webinar of 2024 for FCSI APD. Yeah, we're very pleased to have everybody on board. And today's webinar is the science behind refrigeration. So as I said, we're very happy to have Bill from Turbo Air Refrigeration as our expert speaker. Bill has been in the industry for over 4 decades, and he's equipped with an extensive knowledge of his dual expertise of mechanical and electrical engineering. His career has been characterized by a diverse range of roles, from hands-on service and repair to strategic positions involving collaboration with national chains, designers, and manufacturers. Bill's innovative spirit is evident in his contributions to the industry, including his work on developing and patenting a pioneering sous vide cooking unit, which was one of the first in the industry. His focus on refrigeration has led him to collaborate with leading manufacturers and driving forward the state-of-the-art sort of refrigeration solutions. Today, so we're diving into the science behind refrigeration, and we look forward to gaining his insights on how refrigeration works, the technology behind it, and what we're looking for forward into the future of refrigeration. So following, Bill's got about 65 minutes for his presentation. And if you have any questions, please post them in the chat. And then we're going to save about 15 to 20 minutes after for Q&A. So everybody, without further ado, please welcome Bill Smith.
Thanks, Ben. We appreciate having us on here today. My partner, Carlos, is on here as well. We both work for the same manufacturer. What I wanted to cover here today is a program. Now, this is a generic program. It is not manufacturer specific. This does incorporate all of the components for any manufacturer of refrigeration. and a little bit of the air conditioning work. We're going to cover a little bit of theory, basically all different types of refrigeration, walk-in boxes, freezers, and refrigerators. So as we get through this, some of it you're going to be like, what does that mean? I promise you, as we get towards the end, it'll all come together. So basically, you have 4 basic components in any refrigerator, freezer, walk-in box, what have you. You have a compressor, a condenser, the metering device, and the evaporator. And it's just all how we put it together. So let's start here. A couple of things we'll cover is a little bit of thermodynamics, electrical. Why is that important? How does it work? The parts and the types of refrigerant. I was talking to Ben and Jennifer yesterday a little bit about refrigeration, and quite honestly, this is changing at a very significant pace. As new refrigerants come out, new components, electronics now are entering into the industry at an alarming rate in a good way. But don't think of electronics as your app on your phone or OS 17 or 18. Think DOS. A lot of the components still are very antiquated. However, they are electronic and things are changing. Most of the technology today, we'll get into that a little bit later, but is proportional band controllers, and I'll explain that in a bit. So basically, as most of you know, there's 4 states of physics. You have your gas, a solid, a liquid, and plasma. In refrigeration, we're just going to talk about the liquid and the gas, how they work and how they interact. Thermodynamics is a key part here because what we're doing is we're transferring the energy. As you know, it can't be created or destroyed. It's how we transfer it. So one of the things is obviously it's going to go from the hotter component to the cooler component. And how do we do that? It's the way that the refrigeration is absorbed. And a lot of people, they're like, well, I don't understand chemistry. I don't understand this. Well, really, when it comes to refrigeration, here's what I want you to think about. Think of a pot of water on your stove. So first, it's a liquid. You add heat to it, it turns into a vapor or steam. You cool that back down, and it turns back into a liquid. So you're altering the state of that media. And the media is water here. Now, obviously, it boils at a high point. Refrigeration, think along that same line, but what we do is we use the boiling point of the refrigerants for the application. So that's how kind of this all works here. We're not blowing cold air in. We're absorbing the heat out of the unit through a chemical reaction. And we'll show you how that works in a little bit. Electrical is another thing that I get constant calls about, questions. How does it work? What does it do? Basically, in a nutshell, you have the compressor, which you'll see right around the 4 o'clock position. But you'll also notice that there's lighting and switching and a controller. There's many things that control the compressor. We also have many different types of compressors that we'll talk about that are used in our industry today. One of the things, again, is voltage, and voltage is key. I always tell anybody that's specifying a job or, like our professional members here that are speccing the project, check the electric twice before you put it down. A lot of times people say, oh, yeah, they have 243 phase, or they have this. Trust me, pay to have a professional electrician or a competent mechanic or maintenance person go in there and verify that. I would say 1 out of 8 jobs that I get called out on to look at something, it has a wrong voltage of a part in there. So whether it's 110, 115, or 120, they're all the same. 208, 240, and 480. There are 3 different voltages. Now, rest assured, you can run a 208 on 240 and a 240 on 208, but they're going to run a little hotter, and the amperage is going to change a little bit on it. So again, it's very, very important to double and triple check that voltage. kind of this is how it's written. Sometimes you'll have a supply voltage of 110, 115, 120 alternating current AC. A lot of times you'll see 50 or 60 hertz independently, or 50/60. This is another key factor, and I'll cover that in a second as well. So you have this in single phase, and you have 208, 240, 50/60 in 3-phase. And they indicate the phase. You'll see the 3 with the line through the 0. That's how we write 3-phase in the industry rather than spelling it out, just shorthand. The other thing that we talk about is hertz. Hertz is the frequency that the waves oscillate. So to show you how that works, if you look down the bottom here, what'll happen is you'll have this that'll bounce 50 or 60 times a second through the cycle, top, bottom, top, bottom. And you can run a 50 on a 60, and you can run a 60 on a 50. However, there are issues long term. The motors, if they're not dual hertz, 50/60, will run warm. Now they may draw, let's say, half of an amp more than they're supposed to. In long term, you will have failure. And again, I can't stress to you enough, please double check the voltage, especially on the bigger appliances. It does cost a little bit of money when you have to replace a 5-horsepower refrigeration compressor. Anyway, so those are the two big things. Check the voltage, check your hertz, you're good to go. So we have several different types of refrigeration systems that we use in our industry, as you can see here. And part of the test that I give everybody is, what's the first thing you should ask your customer when they ask you for a refrigerator? And they're like, oh, how big, what voltage, what's this? And the first thing you should always ask your customers, what are you putting in it? What item are you putting in there? And I'll explain it to you. We have forced air, obviously, I explained, it has fans. You have low velocity fans. You have a gravity system. Now, gravity systems are used in deli cases, meats, cheeses, things like that. Cold wall, which there's no moving parts. It's just copper tubing that's within the walls of the box that's insulated. And we have a cascade system. Now, you don't see too much cascade system in the commercial end of it. We see most cascade systems in either a blast system, blast chillers, freezers, or scientific units. So let me get back to why it's important to ask. Especially those of you that have customers that system, you either want low velocity or gravity. And the reason is that it's moving air. Air has moisture molecules in it. Those molecules will get on the chocolate and they'll call what's blooming. So it looks like it has all these little white pimples on it. And that's because the air, the moisture is dropped onto the chocolate, refrigerated and cold. It will change the taste. Seafood's another one. Seafood's where you don't want forced air. You would like to either have a gravity or a low velocity in there. But again, these are some things that you always want to talk to your customers about and say, what are you putting in the box? So please just take time to remember there's a multitude of different systems out there. So again, forced air is the most efficient. It's quick, it's fast, it pulls the energy down. Low velocity, gravity, again, there's no moving parts. Now, cold wall is the one anomaly here. It's cheap, it's inexpensive. Again, but what happens is that energy has to come from the sidewalls and work its way into that center pan. So it takes an extremely long time. Anything that's a cold wall system, you do not want to pull down. You want to have the cold product going in there just to maintain it. You'll see these cold wall systems on a lot of wrapped rails. I do see them in pizza prep tables, but predominantly we see them in milk coolers for the schools. So what is refrigeration? Well, like we said, we are basically taking the energy, the chemical reaction of the refrigerant, and absorbing the heat. And depending on where we're absorbing the heat and what state of that process, We either absorb heat or we dissipate the heat. So as we get into the rest of it here, you'll kind of see how this all comes together. BTUs, British thermal units. This is 12,000 BTUs is a ton of refrigeration, or 1 ton. So you'll see that a lot in HVAC as well. It's 2 tons of air conditioning or 2.5 tons of air conditioning. Same with refrigeration. You'll see that. So it's a very common word that we use. These are all the basic parts: the evaporator, the condenser, receiver, accumulator, expansion valves. What we're going to do is we're going to go through this list. We'll show you what each part does, how it operates within the system. And I have not a video, but I have a demonstration model that we'll show you a little bit later. So first off is the compressor. The compressor is the heart of any refrigeration or air conditioning system. Basically, it does what compressors do. It takes a low pressure vapor or gas and it compresses it into a high pressure. So the inlet is called the low side and the high side is called the discharge. You'll note in most of you'll seeing a very large line as it goes into the one side of the compressor and a very small line. The large line is the vapor, and it has to be larger by design because that compressor is trying to pull back a very low pressure vapor to compress it into a high pressure vapor. So the in and the out, that's kind of it. Now, compressors come in many, many different shapes and sizes. The main heart of most freezers is what's called a semi-hermetic, which you have a photo of it here. Now, this compressor, we can basically take apart in a field, like if a valve goes bad or something like that, and repair it. This has oil level in it. This also have other controls where you may have a single head, a double head, 4 heads. We can use this compressor for a multitude of things. They start at a fractional horsepower, say 3/4 of a horse, and I have seen these as large as 50 horsepower on refrigeration system, which is about the size of a car engine. Give you some perspective to that. This is a belt-driven semi-hermetic compressor on a large grocery store chain. It's about a 25 horsepower motor that's driving this compressor here. It's a very, very large system. But again, these come in all different shapes and sizes. So what I wanted to do is give you some scale of reference here as to how big these things can be. The most popular one is the hermetic compressor here, or tin can. These are very small, fractional. They'll start at maybe 1/20th of a horsepower, and they'll work their way all the way up to 5 horsepower. These are done in many different manufacturers. What we look at here is the BTU load of the compressor. Additionally, now that we're using hydrocarbon refrigerants, we have less compression in these. What I mean by some of the compressors initially years ago were, let's say, 8 or 10 or 12 to 1. Today, there may be 4 or 6 to 1 compression ratio because we don't need that much pressure on it anymore with the new type of refrigerants, or basically AKA the hydrocarbons. They're very efficient. We'll show you that a little bit later. Scroll compressors have started to come into the industry in a great amount. We see these in all kinds of things right now, both air conditioning and refrigeration. These are mostly the vertical compressors. They do have a different harmonics to them. But imagine 2 finely machined screws turning together. That's kind of in a nutshell what a scroll compressor is. The other thing that we see today are variable speed compressors. These are in a multitude of sizes. And if most of you have a current refrigerator that you've bought within the last 2 or 3 years, you probably have a variable speed compressor in there. These compressors slow down. They vary the RPM, or revolutions per minute. And a lot of times if you open, like I say, a brand new refrigerator, regardless of the manufacturer, you may hear this spin up because they just basically slow down to keep it, but they're very, very low amperage. The thing that variable speed compressors do, they do work very, very well, but they take a considerably longer time to pull down the component. basically the refrigerator freezer that they're in. The other one that we see a lot more now of is inverter. And again, these are smaller compressors. And what I mean by that smaller is they're fractional horsepowers. Not, I'm not going to see a big inverter compressor that's 10 horsepower. These are generally going to run somewhere between a quarter and 3/4 of a horsepower. Condenser and condenser fans. This is our next thing. So the fans are extremely important in the refrigeration cycle, whether they're high velocity fans, low velocity fans, clockwise, counterclockwise, or electrocommutative motors. We need these to basically dissipate the heat or drive the air across the evaporator to absorb the heat. Now, we also have different types of evaporators, and we'll cover that in a minute, but I wanted you to be aware of the terminology here. So basically, it's CW or CCW, stands for clockwise or counterclockwise. They come in a multitude of different sizes. If they're shaded pole or capacitor start or run motors. But again, now we have ECM motors, which are variable speed as well, and we can reverse direction on ECM motors. Electrocommutative motors or ECM motors are kind of a mainstay anymore. Most manufacturers are using ECM motors for one major reason: to save energy. That is the big key here. The standard motors basically were 9 watt, 10 watt, 12 watt, 15 watt. ECM motors are very consistent and they're very, very low wattage. Rather than 10 or 12, they may be 0.2, 0.3. So most of those, you'll see almost everybody in the industry switching over to ECM motors. So this is a typical condenser. Now the condenser is where we dissipate the heat. And the word condenser is exactly what it says. We're always going to put the inlet from the compressor, and remember that's a high pressure vapor, into the condenser. Now what that does is it goes in the top, and as it goes down, there's generally a fan blowing across it, and that cools down that high pressure vapor. In the condenser, it takes that high pressure vapor and then cools it down into a high pressure liquid. So at this point, we're altering the state of the refrigerant. Think of that again, that pot of boiling water on your stove. So you have the inlet, high pressure vapor goes through the condenser, comes out a high pressure liquid. At this point, when we go from the vapor to the liquid, we're dissipating the heat. We're losing the heat. So this is where the hot air is coming off, and I get a lot of consultants and designers that say, well, what's the BTU load? How much should I design into here? I need to know. And basically talk to whoever the manufacturer is, and if they say the refrigerator is 1,200 BTUs, or the freezer is 2,000 BTUs, that's going to be your dissipate heat load as well. I've got to take the energy from point A and I have to move it to point B. If you don't know, and if it's a very small unit, you can figure on 1,000 BTUs. But some of the bigger 2 and 3 door units or glass door units or something like that, they're going to be considerable more. And again, just check with the manufacturer to find out what the BTU load is. And that's the question you ask. What are the BTUs of the cabinet? That will give you your heat load of rejection. Now, this is a static condenser. There's no fan. But again, as you look at the condenser, you'll see one line that comes all the way up to the top. So the line at the top, the refrigerant inlet line at the top, goes up the top. And as it comes back down, we again take that high pressure vapor and we turn it into liquid. This is on most domestic refrigerators. And you'll see this also on some very inexpensive commercial refrigerators. But we cannot do a very large unit with this condenser. It is basically restricted by the size. So most of it's just medium temp or low temp, but very small cubic capacity. You'd say probably nothing more than about 20 cubic feet. The other thing that I get a lot of calls about are water-cooled condensers and also glycol systems. where this is very, very popular. So again, we have the compressor, the controller, we have a water regulating valve, and a water-cooled condenser. Basically, you have a shell and shell to maintain a specific head pressure. Too much water, it won't refrigerate enough. Too little pressure, or too little bit of water flow, it'll go off on high head because it cannot cool down fast enough. The downside, waste all the water. These are very efficient on how they work, but inefficient for the displacement of the water. So you get a little bit closer of it. So basically, the water regulating valve on it. Evaporator and evaporator fan. So if we have the condenser, which we lost heat, the evaporator is on inside of the unit, and that's where we absorb heat. So once the compressor builds up that high pressure gas, it goes through the condenser, it condenses into a high pressure liquid. It'll go through a metering device, which we'll cover in a second, and ends up in the evaporator. Now, the evaporator is always going to be the piece that's inside of the cavity, the unit, or inside of the walk-in box. And basically, sometimes these are coated. You can have a multitude of colors for black, gray, a blue, a clear. But most manufacturers coat the evaporator to prevent the acidic vapors of the products from eating into it. Anything that has a high acidic value, lemons, tomatoes, mayonnaise, ketchup, the vapors from that love to eat aluminum and copper. And during COVID, one of the main reasons that everybody was buying refrigerators and freezers, because they let them set so long empty, and there was enough acidic vapors in there that they just ate the evaporator apart. So here's a shot of the evaporator. Now you can see an inlet from the capillary tube, which is a metering device, and the suction side out to the compressor. And you'll notice that they're two different sizes. Again, the capillary tube is a metering device, which puts in a very high pressure liquid. But by the time it comes out, it is a very low pressure vapor. So as you see the two different sizes of the diameters, again, we need that larger size on the suction size to pull that vapor back. But on the top here, you have a shot of an epoxy coated evaporator. Now, this is a static evaporator. It does have an in and out. There is no fan. You'll find these a lot in very small domestic refrigerators, or like in your hotel room when you check in and there's a refrigerator in there. There's a very inexpensive way to do it. It does take time to pull down on the pressure, and we generally cannot go up very big on these because they're just inefficient and take too long. So basic parts of a refrigerator. Well, we have an accumulator. That's a big one here. Now, the accumulate does what it says. It accumulates any liquid refrigerant. Why? Because it has to boil off that refrigerant to pull it back. Remember, we cannot compress a liquid, but I can compress a vapor. And the accumulator, I got a shot of one here, which I'll show you in a second. These are out of line. But you also have a receiver. So the receiver, think of that as the gas tank on your car. Now, receivers are used on expansion valve systems. As the expansion valve closes, the refrigerant or gas has to have some place to go. That's why you're always going to have a receiver on that. As the expansion valve or TX valve throttles down, it backs that refrigerant up in the system. And if it didn't have a receiver on it, by the time we would throttle it all the way down, we would probably be breaking the valves in the compressor because it would back up. So here's a good shot of it. You have the inlet and the outlet on the accumulator on the right, on the left, and you have a receiver on the right. The receiver has a service valve, so we could put a gauge, refrigerant gauge on it. We can check the pressure. We can also see what's in there. You'll note that little small little flare nut there that we can access it with. That's generally going to go to your refrigerant line. On the top, that nut would come off and that would go to whatever device that you want it to. The bottom unscrews and there's a 1/4-inch ratchet like thumb screw in there that the service technician can take a service ratchet and back front forward or back forward that valve for access to the receiver. So the metering devices, we did talk a little bit about this. The metering device is critical. Now think of this as the carburetor on your car, whether it's a capillary tube or a TX or expansion valve. This is the part of the refrigeration system. As it comes out as a high pressure liquid, it's going to go through a metering device. That metering device is then going to restrict that flow into the evaporator. Now, a cap tube, which I have a photo of that I'll show you in a second, is basically a piece of tubing that is a given length in size and a given internal diameter. Generally, they may be 1/64 of an inch internal diameter, and they could be 6, 8, 10 feet long. Whereas an expansion valve that will meter the amount of refrigerant that goes in on the outside or discharge of the evaporator and will automatically open and close. We use an expansion valve basically for freezers and refrigerators. It is an expensive system to put in, but extremely efficient. Why? Is because I can meter more refrigerant into the evaporator quicker to pull the refrigerant, the heat out. Whereas in a capillary tube is just like your hose that you have at your house. And we've all had short hoses and we want to go wash the car. So you put another hose onto it, but the pressure's not the same. In a capillary tube, what happens is that pressure's, no matter how much pressure is on the end of it, you're still only going to get X amount of pressure at the end. And it oscillates just like the Hertz, up, down, up, down. Whereas an expansion valve, as that opens and closes, is a specific but steady increase in refrigerant or decrease in refrigerant. So let's show you how they work here. These are the parts of a thermostatic expansion valve. In the trade, we call them TX valves. There's a multitude of parts that are in there. Obviously, we have a strainer on the inlet. You'll notice that there's 2 push rods, an element at the top. We have a spring on the bottom, which gives us an opposing force to the thermostatic head, and it allows the refrigerant in. So this is kind of a cutaway of it, what it looks like if you were to slice it in half. You'll see the push rod or ball, and that, depending on how the system's adjusted, what type of refrigerant, what application it is, will allow the refrigerant to migrate into the evaporator. So here's just a real quick demonstration. You'll see that the bulb, the red fluid in the bulb, is a gas. Now, this bulb is generally attached to the discharge or outlet of the evaporator. When the system is satisfied or it's close to temperature, it'll turn back into a liquid, and it doesn't put a lot of pressure on the power element or the head. When you have a situation where it needs refrigerant, it turns to a gas, creates a higher pressure, puts a higher pressure on the rod, and opens up the valve to put more refrigerant into the evaporator. We do see a little bit manufacturer have these in like self-contained reach-ins. Mostly where you're going to see this is walk-in boxes and HVAC systems. And that's a cap tube. That's what a cap tube looks like. If you stretch this out, it's 6 feet long. So the capillary tube with a tin can or hermetic compressor is the most inexpensive way to make a refrigerator. Everybody makes a system just like this. You'll have these at different types of refrigerant. And again, depending upon the application, how big the box is, what type of refrigerant, these could be in a multitude of different lengths and different sizes. So the key here is you have two basic types of metering devices that go in. What I wanted to point out here today is also that you have electronic expansion valves that are out there that can be adjusted. There are some manufacturers that tie the controller into the electronic expansion valve that they can meter the amount of refrigerant going in or adjust it at peak times. The one that I showed you here was a static expansion valve, which it does it automatically based on the temperature sensing. Again, that's on the discharge or the outlet of the evaporator. Another term that you may hear is filter or filter dryer. Now, this is a very key, critical part to every refrigeration system. Every manufacturer uses some type of filter dryer in it. And basically, it's aluminum oxide that's encapsulated in some type of device. The key part here is it pulls out any moisture, and it also pulls out any impurities that are in the system. The reason that this is so important, especially on the larger systems that a lot of you specify, grocery stores, big walk-in boxes, if you get any leaks in there and it pulls water into the system, you could have serious catastrophic failure with the compressor. The filter dryer is your first line of defense. Think of that as the filter in your house for your air conditioner. When it's dirty, you have to change it. And what's that doing? That's preventing dirt and dust from getting up in your air conditioner. This is a permanent thing in the system that actually helps prevent moisture and debris. And what I mean by that is when, as a manufacturer, we solder up the joints that go into it, most of us are using some type of nitrogen or some other device that are blowing it through the line to prevent any oxide on the inside. However, when you're putting a system together, it doesn't matter who does it, what manufacturer, and I'm not saying anybody does that, but let's say there's a micro piece of dust that's in there that gets in the refrigeration line. That filter dryer is what's protecting the system. And generally, they will stay in there for the life of the system unless there's some kind of failure where you have to replace a compressor or something goes bad. So this is what they look like. Now, you have a solid core and you have a beaded core. And these come in a multitude of sizes and shapes. They can be as small as a thumb drive, and they could be as large as 2 cans of coffee. These are rated by diameter of the pipe, the tubing. Refrigeration, we generally use an OD versus an ID in we use an ID versus an OD that they would in plumbing. However, you'll have the solid core here, and then you also have a beaded core. And you'll see on the beaded core here, it's, again, the same dioxide, it's just the way it's componentized. One thing to remember now, all of these, they do store some type of, a little bit of refrigerant in a filter dryer. So as a manufacturer designer, what we do is we look at how big a filter dryer we want and how much refrigerant is stored in here that it takes to process through here. And then we add that into the charge of the system. So a small system may hold very, very small ounce milliliters, but a larger system may hold 6 or 8 ounces in these dryers. And again, they come in multitude of shapes and sizes. A sight glass is another term that you may hear. Basically, we can see what's going on in the system. That little indicator down in the bottom, they'll come out of the box yellow, but they'll turn green quickly. Once the system's up and running, we want to make sure that they're green, which means that they're dry. Yellow indicates some moisture. You'll see these basically on the bigger systems. You will not see these on small, self-contained reach-in refrigerators. The larger systems, supermarket, grocery stores, walk-in boxes will have this. And what the technician is doing is he's looking for refrigerant flow. So generally, what'll happen when it starts up, you'll see some bubbles in there that'll pass through. Once that clears up, you'll know the system's full. A technician will look at that if it's in there the first thing, and the call is going to be the system's not working. So he's going to, or not cold enough for you, or not maintaining temperature, and he's going to look to see what color that is, and if it has any type of bubbles in the system. So there's a lot of little components here that go together to make the system do what it does. Thermostatic expansion valves or TX valves, there's all different types, internal, external. We go by what type of refrigerant it is. We also have to know how many tons of refrigeration. So when someone comes to me and say, I need a box for whatever product I'm putting in, I look at how big the box is. I'm like, what are you doing? What maintain temperature that you want to maintain of that product? Sometimes when you're doing a box, I might have to go to a 6 or an 8-inch wall, depending on what temperature and what the customer is wanting to put in there. So again, these are all things that you have to look for. So superheat's another one. And I know I'm throwing a lot at you guys here, but these are basic terms that we use in our industry every day. Superheat, we're adding heat to the vapor. Why do we want to do that? So we don't have liquid that's getting pulled back in the inlet of the compressor. Remember, it cannot compress a liquid. We can only compress a gas. The problem so many times is that if you get a compressor that'll pull back liquid, chances are you're going to blow the valves out of it or the pistons or something like that. And it's a very expensive mistake. Superheat's kind of critical too. We generally look for plus or minus 10 degrees on superheat. The reason that is we want to make sure that too much superheat, the system becomes extremely inefficient. Too little superheat, the system's, again, inefficient, but it's pulling back liquid. We have to find that right balance between vapor and liquid at that point. So that's what the term superheat means. This is kind of a basic overview of a cap tube. Yeah, the compressor comes out, goes through the condenser. Remember, high pressure vapor out, excuse me, high pressure liquid out of the condenser. It'll go through the dryer to clean it. Then it goes through the capillary tube into the evaporator. Again, that high pressure liquid, once it hits the cap tube, that's our junction point where it starts to turn, again, in the evaporator from a liquid to a vapor. At this point in the evaporator, we absorb heat. So basically, through the chemical process of absorption, we either dissipate the heat in the condenser and we absorb the heat in the evaporator. If you look at an expansion valve system, you'll note that receiver that holds the excess refrigerant. Again, it goes through the refrigerant dryer, through that expansion valve, back through the refrigerator. And you'll notice on the outlet of that evaporator have the TX bulb. That bulb is sensing the temperature on the suction line or low pressure side that's going back into the compressor. What that TX bulb is doing is telling the TX valve to open or close. And that's how we're able to put so much refrigerant at one given time in there. Now, we're not flooding it, but we're putting enough liquid refrigerant in there that we can absorb heat on a very quick and efficient way. This is kind of the highlight. Same system, but basically you have the high pressure, condenses, high pressure liquid. The liquid goes through, again, the metering device into the evaporator. And at that point, it turns into the low pressure vapor. Now, remember, on a refrigeration or air conditioning system, you have one big line and one small line. Head pressure or high, low side, or suction and head pressure. Think of the suction line as a straw that's you're trying to suck a milkshake or something thick and creamy. If you have a real small straw, you're not going to get enough suction on it to pull it through. That's why you need a larger straw to pull some volume through there. Some of the different types of connections and fittings that we use on our industry, we have sweat, where basically we take two components and solder them together. In our industry, we like to use a 15% silver solder, which makes a good connections, also stands up to high pressures and high temperatures. As you can be aware, we talked about high pressure, high temperature on there. Pressure and temperature are directly correlated with each other. If we use something less than a 15% silver or like a 50-50, it would heat the joint up and the connections would leak. We also have what's called a flare system. This is very, very popular. Filter dryers, expansion valves, what have you. This type of system is where we can connect the two together. You'll see the edge has a bevel on it as well as the flare. And what happens is the technician will put a piece of copper tubing in here. We use a special fixture to flare out the end. So the copper tubing will sit in the nut or the bonnet there. And then that tubing is between the flare head and the cap. We tighten that up, and that's what makes the connection. The other type of connection that we see a lot is called zoom lock. This may have a few other trade names out in the industry here. This is basically a hydraulic pressure that's crimping the fitting on. Now, these are really good in an application where you cannot have an open flame or open torch, or very tight locations. These zoom lock tools do a fantastic job. For the technicians that are out there, they love them, but I can tell you that this is not a cheap setup. A good zoom lock setup that covers a multitude of sizes, you're probably going to have about 3,500 pounds just for the kit. Schrader valves, another one. This has been around for a long time. You also have these on your car tires. But basically you have the housing, the core, and the cap. This is where the service technician would take his gauges and hook into here. He tighten it down, and this way he can read the pressures. So you're saying, okay, that's great, but what does that mean? Well, let's take a look. So that holds the refrigerant back, that valve. And refrigerant or Freon is the chemical that we use. Now, remember earlier I said that think about that pot of water. So in the refrigeration industry, we look at different types of boiling points. And let me show you what I mean here. We have hydrocarbons, natural refrigerants. Olden days, we had chlorofluoromethanes, which was 12-502. These were the bad ones. These had chlorine in them. These were the ones that everybody got upset about, that were depleting the ozone. A chlorine molecule, if I remember chemistry right, will destroy like 100 oxygen molecules before it eventually burns out. This is also the very nasty stuff, 12, 502 and 11, 500. When they were exposed to gas, creates phosgene, which will kill you. This is, we don't use these anymore. These have been banned since, I want to believe, the late 90s. But there's still some systems that are out there. The hydrofluorocarbons were used. The R22, which is used in a lot of air conditioning systems, they're still nasty and being phased out, at least here in North America. Hydrochlorofluoride, which are the replacements of 134 and 404, they're replacing 12 and 22. But again, these are bad because they're azeotropic blends. What I mean by that is they're different chemicals. I'll show you that in a second here. And hydrocarbons. Hydrocarbons are what you're using today. The beauty of hydrocarbons, whether it's propane, butane, isobutane, or a blend, they're extremely efficient. The beauty of hydrocarbons is that we can do the same job with a third less, or maybe even half. So if you take just a standard, let's say 23 cubic foot refrigerator, you look at that 23 cubic foot refrigerator, and 15 years ago, it may have had 12 to 15 ounces of 134 or 404 refrigerant in it. Today, with R290, 600, 600A blends, and some of the others, we can do the same job with about 2 ounces. They're that efficient. This is kind of a chemical makeup of 134 and 404. And as you can see, this is pretty nasty stuff. These are bad for the ozone. Most of the technicians, at least in North America, had to recover these as they were extremely toxic to the environment. As you can see on the 404, that is a blend of a multitude of chemicals that's spun down. and they're nasty. I'll be honest with you. I'm happy to see these go. 404 and 134 had some unstable characteristics at different temperatures. And ironically, what many people don't know is that most refrigeration systems operate, the temperature of the system itself is around 200 to 225, 250 degrees. When the condenser gets dirty and it cannot breathe, which causes the head pressure to rise, and it causes a little bit more amperage, these molecularly break down the POE oil, which breaks down, it's called stiction, at 350 degrees Fahrenheit. So you have a very tight, narrow window on these things. And they caused a lot of problems. They really did. One of the takeaways that I'd like you all to remember is always make sure that the condenser is clean. Think of that condenser as the radiator on your car. Certainly, we all have hot times wherever you may live. So pick the middle of the summer, and would you put a piece of cardboard in front of the radiator and drive down the highway? How far do you think you'll get before the check engine light comes on? The same thing applies to refrigeration and air conditioning systems. If that condenser cannot breathe, you're going to have some very serious problems with it. So hydrocarbons, this is the beauty. Hydrocarbons are very unique, and you'll see either butane, an isobutane, a blend, ethane, propane, and CO2. Now, what most manufacturers are going to is propane. Isobutane is probably second, butane a close second, and CO2. Now, it's the same CO2 that we use in soda systems, but it's operated on extremely, extremely high pressure. And let me show you this next one. This is the boiling points. So you'll see CO2 has a negative 109 Fahrenheit, which makes it ideal for any type of application. Butane and isobutane are right there, but propane is the sweet spot. So you will see propane used in both refrigerators and freezers. It has a extremely excellent boiling point, and that's how we design our systems. We basically look at what we're putting in it, what we're told to build. We design that system, and we look at the boiling points of the refrigerant, and we say, this one works. Now, again, today, everything, different manufacturers have different applications. They're going to use different controls for a specific project, and we're going to cover that in a minute. So I just want to give you kind of the beauty here of propane. Now, do not think propane like on your grill. Think medical grade. There's no mercaptan in this. Mercaptan is the odor, rotten egg smell that's in there. There's no moisture in this. Whereas if you go buy your propane at whatever your supplier is, you could have impurities, you could have some MAP in there, it could be a few other different gases, and there's always a little bit of moisture in that. Now, in North America here, we can only use a maximum of 150 grams of propane, or 5.3 ounces. Propane has been used for decades outside of the US. And what has happened is obviously when the Montreal Protocol and all that took effect, the manufacturers were like, we got to find different refrigerants. Now that we have the Department of Energy into it, things have, it's made us all change the way that we go and do business. So we have to follow these guidelines or we cannot manufacture the unit. Now, there has been talk for about 2 years of going to 500 grams of refrigerant in the system. And what you'll see is most manufacturers will do on the very larger boxes, we're going to have 2 separate compressors. We have one evaporator, but it has 2 passes through it. And the way the law is written, we can only use X amount of refrigerant. Now, this doesn't apply to other countries and things like that. Again, this is only in North America, but I wanted to make you aware that we're doing a job with very little refrigerant in the system. And some of the manufacturers have been doing it for probably 20 or 30 years. Most of you that have a motorhome, travel trailer, or coach, you've got a propane refrigerator in there. System controls is another one. Now, this is taking leaps and bounds where this is changing almost weekly. There's built-in analytics. There's pressure controls, high pressure control, low pressure control, inlet valves, sensing boards. This is amazing as how much this is changing. Earlier, I mentioned that it's a proportional band controller that most of us are using, and that's most every reach-in manufacturer. So what that means is that when the system's running, we have a multitude of RTD probes or resistor probes that are in the unit. We'll generally have one buried in the evaporator so we can sense temperature. There will also be another probe that's buried maybe in the airstream, either the inlet or outside of the box, so we can test it. And the way that a proportional controller works is, let's say the unit's 50 degrees. I know I've got to come on. As the system's running and it comes down, it may shut off for a little bit of time to check the drift. How much further can I come down? Then it'll come back on. And it may do that 2 or 3 times, but again, it saves energy. And this is what most manufacturers are trying to do today, give you a good product and save you a little bit of energy. So you kind of see these different types of controls out there. Now, controls look different. There's different manufacturers. They do different things. But again, think DOS. This really hasn't caught up to today. As of last week, I was talking to another manufacturer, and they are working on a Bluetooth-enabled system that actually they can do this remote. Now, this has been working on for some time. The biggest problem here is nobody's using the same language on the software. And it looks like this may come to fruition here to where whether you have an Android or an Apple phone, that you can download the app and control it from that. I believe sometime by the end of this year, most manufacturers will have some type of Bluetooth-enabled system that they can use. So what are the controls? What do we? Well, we monitor temperature. We monitor pressures. We don't want the system to run too low or too high on pressure because we could have failure. Too low, it could be out of gas. Too high, we could have a restriction. We also measure oil pressure. This is another important controller. Now, most of these you're going to see on larger systems, not the small single and double door commercial refrigerators that are out there. But I wanted you to make you guys aware of that. We also have voltage controls. Depending on where it's at in the world, I have noticed that there are unstable voltages where they drop in, they drop out. And depending upon the controller, this is very important because if the system drops out or the grid drops out, and this unit tries to come back on, it could hook the compressor, basically cause the compressor to lock up. You have solenoid valves that allow refrigerant to go in and out. This is done on a lot of different units, basically shuts the unit down, especially walk-in boxes. So the pump down valve, we shut the solenoid off, let the system pump down, and it goes off on low pressure. Expansion valves, we talked a little bit about that. Defrost timer or time clocks are important. You'll see these on most of the bigger systems. They have been used on small single and double door freezers up until the electronic controller was put in there. Electronic controller has a lot of application, and there's a lot of ways that we can use that. So again, remember I was talking that it kind of in DOS. Electronic controllers basically have about 120 petitions or 100 different types of things that they can do. But most manufacturers are only using 20 or 30 of those petitions that are in there. And again, there's so many different manufacturers of controllers out there that do different things. And the last thing is defrost heaters. Excuse me, whether it's a pad heater or a rod heater, especially in freezers, we need to defrost the coil. Almost all refrigeration systems, whether it's a walk-in box or a reach-in freezer, will build up ice on the evaporator because we're dealing with low temperatures. We have to defrost that. If we do not defrost and get that ice off of there, eventually the ice will build around the evaporator housing and the system will shut down because we can't move enough air across it. And it builds up to a big block of ice. Refrigeration gauges. This is what your technicians is looking at. So you could have 2, you could have 3. These are basically D'Arsonval movement, but today you can also get electronic gauges that are out there. In all cases, the red side's always going to be the high side, the high pressure, and the blue will be the low side or the suction. You'll notice here that they are set up based on different types of refrigerant. So depending upon the refrigerant, all the technician has to do is look at the gauge and look at the pressures. Those pressures, again, are correlated to the very specific type of refrigerant that's used. Most all manufacturers should mark the unit as to what refrigerant they're using so the technician knows what to do. Obviously, we wouldn't want to assume anything. So a good technician is always going to check to see what type of refrigeration is in the system. Package systems. We're getting there, guys. We're getting there. This is the last part we're going to cover. Package systems, what I mean by that, these are the refrigeration evaporators and condensers that go into the walk-in boxes. Thin mount, top mount, wall mount, center mount evaporators. Again, ask your customer what he's putting in there. These are critical. You do not want to put the wrong application. Indoor condenser, outdoor condensers. You'll see the indoor condenser is generally open. The outdoor condenser has a doghouse or a shroud around it. That's to protect it from elements. Package systems. Package systems are all inclusive. Excuse me. Everything is in this component. Generally, you're going to cut a hole in the top of the walk-in box and drop this down. You run power to it, and everything is inside of that. Again, these are based on physical size, but the BTU load of the box. That's why it's always important. Ask your customer, what are you putting in the box? These only go up to about 45,000 BTUs. You won't see this on a massive, giant walk-in box like you have at a grocery store or something like that. Winter controls. Winter controls are another one. Again, this is for the condenser. Basically, we control the crankcase heater. We got to keep the compressor warm. For those of you that live in a cold environment, the refrigerant will always migrate to the coldest spot in the system. So we keep the compressor hot, or it's warm, to keep the oil within the compressor. Obviously, you wouldn't start your car up with no oil in it. Same thing applies here. The condenser, we cycle the fan control because we want that to come on at about 140 pounds. Any sooner than that, and it will pull back liquid refrigerant to the compressor. Obviously, adjustable pressure control. The doghouse that we talked about. The membrane for the boot of the roof. Again, where are you putting this unit? What are you putting in it? What's the application? In extremely cold areas, we use a very large receiver to hold the refrigerant when the system's not running. Recap. What are you putting in it? Is it inside? Is it outside? With a floor? Without a floor? Are you putting it on a pad? Is that pad heated? How thick is the pad? Are you using 3,500-pound concrete? These are all different things that you have to make absolutely sure when you're talking to a customer that you recap with them. Because again, I have seen so many pads fall apart, wrong types of systems, wrong construction. It can really cost you a lot of money in the end. This is kind of just a quick overview. Remember the compressor, you have a high pressure vapor, goes in the condenser, high pressure liquid. Generally go through a filter dryer. Again, there's a couple different types. There's a sight glass. You have some type of metering device That metering device is into the evaporator. This is where that takes that high pressure liquid to a low pressure vapor. I'm absorbing the heat, and the cycle continues. Refrigeration systems can be in a multitude of sizes and shapes. Important thing here is to always ask a lot of questions, double check, make sure, check your electric, and hopefully you'll have a pretty good application here. Okay, we're going to open this up. If you guys have any questions or answers, or if we've all had it, let's just bail out of here, and I'm going to turn this back to Ben.
No, thanks a lot, Bill. That was very informative. I think just seeing some of the comments come up into the in the chat, I think everybody seems very pleased with what you've presented so far. I'll just go with some of the questions. I've got David George at the question here. Why do they limit the total refrigerant to 150 grams for propane?
That's a good question, and you thank our federal government. You know, we didn't have any limits when it was something else, but the minute everybody went over to propane or butane or isobutane, the Department of Energy, the EPA get involved and says, we have to regulate this. You go other places and there's no limits. It is just one of those things where the federal government's got to get their 2 cents out of it.
Okay. We've got another question from Mark Minnis. When would you recommend a tropicalized system?
Well, I'd have to look at the application. This is one of those things, I got a lot of questions on this one. I can't give you a Kodak moment on that, but it is application. What are you putting in it? Where's it going? And then we can go from there. No, this is only on the 150 grams is only applied for self-contained systems, not remote systems. Sorry about that. I wanted to clarify that.
That was just a follow-up to Andrew's question regarding the limit applied to external compressors, correct?
If I read that right, that would be package systems. Yeah, that's not applying there because it's not a self-contained.
Okay. So going back to, say, tropicalized systems, you said you would be using it, you'd have to kind of know more of the application and what you're actually putting in the refrigerator before you could recommend.
I got to know where it's going, what they're doing. You know, a lot of people like, why are you asking all these questions? The reason I ask all these questions is because I want to make absolutely sure I'm clear on what you want or what you expect. And then I can go from there.
Okay. We've got another question from Mark Fetting. Which is more efficient, air drawing through a condenser or air blowing through a condenser?
As long as the CFM or cubic feet per minute is efficient in both ways, you won't have a problem. There are some manufacturers that have a cycle where it'll, let's say it'll reverse direction or something like that. That's not very efficient because it only limits it for a given time. And on an ECM motor, the blade, the pitch of the blade, you can't change. It's not a variable pitch, it's a variable speed. I prefer, it doesn't matter where it's blowing across it or pulling it through. Again, the key here is to make sure that you have a consistent cubic feet per minute, whatever that's designed to do. We know as we're designing in the system about how many CFM across the evaporator that we have to pull.
Okay. We have another question from Larry. When and why would you recommend a water-cooled system?
Good question, Larry. Water-cooled systems were originally designed for extremely hot applications. Not so much in a, let's say a restaurant, but you have no air movement, things like that. We do see a lot of them that are still out there and in use. Now, this could also be tied into a water tower where the water is cycled through a tower rather than dumped down the drain. Years ago, we did see a lot of ice machines, the larger ice machines, 1,500 pounders, that were using a water cooled. But in today's environment, water cooled systems are kind of going away. and I'm seeing more glycol systems go in.
Mm. What's the reason for that? Why do you see the change?
Cost of water. A lot of countries that, especially here in the U.S., water is very expensive. In Arizona, it's a very highly sought after commodity. Gets a little warm out here in the summer. I don't see very few water cooled systems. I will see a few water cooled systems around the coast where they do have access to water. But again, the cost of the water, it's just going right down the drain. Where you do have a lot of water cooled systems is in larger air conditioning, hotels and things like that, where they're tied into a water tower where that water is being constantly recycled.
So in areas where water is cheaper, you'd see more water-cooled systems. But like you said, in places where you have droughts like California, Arizona, I'd imagine even Australia as well, you'd see more glycogen or glycogen or glycol systems.
Glycol systems. That's a I didn't cover that, but that's another system all by itself.
Okay. We got another question here from Christian. How would you decide between a TX valve controlled systems versus a capillary tube system?
Good question. Capillary tube systems, I generally see most of those on inexpensive or commodity boxes. It does not cost a whole lot of money. Your expansion valve system does cost a little bit more money to do that, but it's very, very efficient. So, if I have a customer that, let's say it's a hospital, and as we know, they have large kitchens. They're also doing a great number of meals through there, healthcare, what have you. I definitely have a TX or expansion valve system on that. Whereas, your average mom and pop that buys a refrigerator for whatever, that's generally going to have a cap tube system. But if you talk to any technician that's out there, an expansion valve is the way to go. It's extremely efficient. I could have an expansion valve box and a capillary tube box. Same cubic feet, same refrigeration system on both. Just one's a TX valve, one's a capillary. What I mean by that is, but let's say both of them are quarter horsepower, 2000 BTU systems. That expansion valve system will pull down faster and maintain temperature longer than a cap tube in a very short time.
Okay, great. We got a couple more questions here. Mark's got a question saying, would you support the practice of staggering defrost cycles so refrigeration units are cycling out of sequence?
Yes, and I've done that on large walk-in systems, especially some of the bigger boxes. The largest walk-in I put in was probably 200 by 200 by 2 stories tall. We had 4 systems in there, and we staggered the defrost on all of them to maintain temperature. So 2 would come on, 2 would cycle off. Those 2 would go off, the other 2 would come on. Again, it's the application. The customer had a very delicate food item that the temperature range he only gave me was 15 degrees. So yes, you can do that, but again, it's all in timing and how you sequence the system to go into defrost.
Okay. If a food and drink product is to be at 2 degrees consistently in a chiller, is that possible? As the air temperature is always changing and depending on how many times the doors are opened and closed.
That is correct. So 2 degrees is we do see this in our scientific community, but 2 degrees is pretty tight. Generally, I'm going to see a little bit tighter band or wider band than 2 degrees in that. You are correct, but if 2 degrees is exactly what their customer wants, I would have it in a bath within the system. Basically like a pan within a pan. I have done this in scientific coolers or chromatography units where the customer wanted a very specific temperature range. Honestly, the most I could get was 5. But I had a bath in a bath. So like a double boiler here. And it worked pretty well. I mean, they were happy with it. It was a research lab.
When it comes to something like a wine fridge where you need to keep, say, champagne at like a 6 to 8 degrees or something, I mean, you see what is usually that range you have if doors are frequently open? Is it a 2 to 3 degree range you look at?
Well, for a wine cooler, depending on whether it's a red or a white, obviously they're at two different temperatures. But the electronic controller, you can go in and adjust that controller to get it down to within a reasonable range. And on wine, obviously because it's in a bottle, there's a couple things here. One, you want to make sure that the lighting in the box is critical, because certain lights will affect the wines. That's why some
Mhm.
wines are in a clear glass and some are in a green or a darker colored glass. But my point being is you can adjust that. The time that the box is open or closed really doesn't matter that much, because that temperature, there's so much energy that's stored in that bottle. Let's say if I have the door open for a minute, it really won't affect it that much. It's the controller's job to bring it in. So if I wanted my red wine at, I don't know, 50 degrees, I could set the controller up to do that.
Mm. Okay. We got another question here from Andrew. Andrew from FCSA here. We often spec glycol systems, especially for large installations. We are often questioned by the kitchen refrigeration contractor who want to change it to a DX system. What would be your opinion on the two systems?
Well, that's a great question. Again, my first question is, what are they putting in it? I got to know what's going on here. Glycol systems are really good. Now, glycol systems, again, there's another whole class on that one, but glycol systems do require some maintenance over the time. Frequently, I've seen glycol leaks. I have also seen glycol dissipate on certain things where you've got to kind of go back in and add some glycol. Additionally, you may, depending on what type of glycol and what it's going through, is go back in periodically and let's say change the glycol. DX systems, again, it's the application of it. Now, glycol, you're going to have more surface area to pull it down. DX systems, again, I got to know what's kind of going in on it, what it is. So when you have somebody specify a glycol system, I would ask them, why do you want a glycol system? What's it for? Generally, the bulk of the glycol systems that are out there or are for beer systems and self-serve ice cream, which they work pretty well. But again, it's the type of application and what's going in it. And I ask these questions because I really want to know why it's being specified. Why do you want it that way? I'll sell it to you, but I want to know why you want it that way. And what I always do is I'm like, you're paying a lot of money for this. This would work just as well.
Andrew's got a follow-up question to that about what kind of system you do for a large convention or a hospital. Would it have any number of products or packaged beverages, vegetables, meat, prepackaged meal, any type of system you'd recommend for those types of projects?
Well, I would need to know what boxes that they're going. Is it one box? Is it a multitude of series boxes? A lot of times you can have large systems and zone those valves out there. So what I mean by that is you could have, let's say, one 10 horsepower compressor, and through a series of zone valves, I could bring on and operate different boxes at different temperatures. We also have digital iris compressors today that will have loaders or unloaders on them. The compressor could run at a given RPM. The minute it senses temperature, it'll throw another valve on or another valve again, and then it would operate at a higher efficiency, again, put more BTUs in there. So I'd have to let a little bit more, but that's another application that I would do. Most large hospitals that I've seen are tied into a water reclaim system or water tower where the refrigeration packets are tied into that. They go up on a water tower, either up on a roof or in a building. I've even had them tied into a lake that's out in front of the system, out in front of the hospital, and that's their water recirculation to cool the refrigeration packets down.
Interesting. Okay. Is there any further questions? Or I think we're almost at our time limit for today, but I think we've had a very good engagement. Yeah, thank you for keeping this within about the 65-minute or so time. We've had about 45 people, I think, join today. So thank you very much, Bill. Just for everybody still remaining on the call, just as a bit of an update towards the end of May, we're also having a networking event in Kuala Lumpur. We're inviting obviously all FCSI members, but also other industry members who are not part of FCSI. So Jennifer and I will be sharing some more information about that early next week about in terms of the program, ticket costs, and things like that. So unless there's any further questions, I think thank you everybody for participating. We'll be sending over a recording of this video following today's webinar. And a big thanks to Bill again for your time, and appreciate you calling in from the States this evening. And I look forward to seeing you in Austin in a few weeks at the FCSI event there.
My pleasure, guys. Thank you all for your time. Have a great week.
Yeah, thank you, everybody. Highly appreciate it. Thanks, everybody. Take care.
Thanks, Ben. Thanks, Bill.
Thanks, Andrew. Take care.